Hello and welcome to this video about dead space. We'll be covering a number of broad brush themes. It's a popular topic of the FRCA and indeed was the Viva question I had in my final. We'll be going through what is dead space, a generic definition. We'll look at why it's important and what implications it can have physiologically. We'll focus on some key definitions, and again there's some important definitions to remember and be very clear in your mind as to the different constituents of dead space. And then we'll go on to look at these constituents and look at how we might measure them and what methods or equations might be employed. And a starter for 10 in a Viva question may well be, what is dead space? So the generic definition of dead space is that dead space is the volume of airways in which no gas exchange occurs. Important point to pick up on, an important phrase here is no gas exchange occurring within this volume. So if our dead space volume becomes abnormally large, we'll have issues with gas exchange. And why might this be important to us, and particularly in anaesthetics? Well, we need gas exchange to occur in order for oxygen to get into the circulation. We need it to occur in order for CO2 to get out of the circulation and then avoid hypercapnia and a respiratory acidosis. And from an anaesthetic point of view, we also need gas exchange to occur if we're delivering our anaesthetic via a volatile route. So if we're using cefaflurane, desflurane, etc., then high volumes of dead space or high dead space fraction could impair our ability to deliver an inhalational anaesthetic. And this brings us on to some key definitions. So we've seen in a generic sense that dead space is described as the volume of the airways in which no gas exchange occurs. But there are three very specific definitions which are used to describe dead space. The first of which is the anatomical dead space. And this is the volume of the conducting airways with no respiratory epithelium. So this goes from the nasal cavity down to generation 16 of the terminal bronchioles. In adults, it's roughly about 2 mils per kilo. So for an average 80 kilo male, this would be roughly 160 mils of anatomical dead space. And this is the volume that we measure using Fowler's method. The next constituent is the alveolar dead space, and this is the volume of alveoli which are ventilated but not perfused. We'll go on to talk about this in a bit more detail in a second, but in essence this is where gas is going in and out of the alveoli, but there's not an associated pulmonary capillary perfusion in order for gas exchange to occur. And then the total is referenced as the physiological dead space, and this is the summation of both the anatomical and the alveolar dead space. So a really important equation to have clear in your mind is this one here. So the physiological dead space equals the anatomical dead space plus the alveolar dead space. And to slightly elaborate on the explanation of alveolar dead space, i.e. the volume of alveoli that is ventilated but not perfused, it's worth considering the ventilation-perfusion relationship graph. So if we explain our axes first of all, on the y-axis we've got flow in litres per minute, which will be relevant for both ventilation and perfusion. And on the x-axis we've got change in area of the lung. So we start at the bottom of the lung at the base here, and as we go from left to right we end up at the apex of the lung. If we look at what that does to the trend on ventilation, we see that ventilation reduces as we go from the base of the lung to the apex. A full explanation of this is given very clearly in West's respiratory physiology, but in essence it relates to the fact that there's a difference in intrapleural pressure as we go from the bottom of the lung to the top. And what that means is that the air spaces at the apex of the lung are already quite expanded and can't expand that much more to contribute to ventilation, whereas those at the bottom have plenty of capacity to further expand. So the ones at the bottom ventilate better. If we look at the trend for perfusion, we see a similar overall trend in that perfusion decreases as we go from the base of the lung to the apex, and this is to do with the gravitational effects of blood flow. But a key difference is the rate in which that decrease occurs, namely that perfusion decreases at a much greater rate than ventilation as we go from base to apex. So then if we were to calculate the ratio between perfusion and ventilation, we'd have a point here about a third of the way down the lung from the apex, where you've got complete VQ matching. So our VQ ratio here will be 1. As we go up towards the apex, we've got higher ventilation than perfusion, so our VQ ratio value increases. And as we go this way, the reverse argument occurs. So if we plot our VQ ratio, this is the line that we generate. Now, With relation to dead space, we said that this is where ventilation is occurring in alveoli that are poorly perfused, i.e. alveolar dead space is this side of our VQ mismatch graph. If we were to go the other way, what we'd have is a situation where perfusion is occurring in poorly ventilated alveoli, and this is the shunt component. So this is picture of shunt is this side of the graph, and picture of alveolar dead space is this side of the graph. And finally, we go on to look at how we measure dead space. So going back to our important equation, where physiological dead space, the total amount of dead space that we have, equals the anatomical dead space, which is the volume of our respiratory tree which doesn't have respiratory epithelium, plus the alveolar dead space, which is the volume of our alveoli which are ventilating but not perfusing. Now, you'd be forgiven for thinking that there'd be a way to calculate this one, a way to calculate this one, and then just add them together to work out what the total is. But it's not quite as straightforward as that, and the reason being is that alveolar dead space is incredibly hard to measure. So we don't measure this directly, but we do have a means of calculating this, and we do have a means of calculating this. The way we calculate anatomical dead space, or the way we work out what our anatomical dead space is by using something called Fowler's method, and this involves a nitrogen washout test, and we'll talk about this in another video dedicated to this method. The physiological dead space can be calculated using the Bohr equation, and again this will have its own dedicated video. So physiological dead space, Bohr equation, anatomical dead space, Fowler's method, and then with a bit of simple mathematics you can then calculate the alveolar dead space. Thanks for listening. I hope that was helpful.